So in today's example, I'm going to take you through another finding the area between curves question. A fairly complex one here. It will take a bit of time, and because of that, I'm not going to do my solution live. I've kind of got it pre-prepared, but I'm going to talk you through it. This would be a really good example to have in your notes jotter as well. So at appropriate points in the video, you might want to pause it and just copy this up in your notes jotter. So you'll see in this example here, we have we've got a cubic. So our cubic function is up here, x cubed minus x squared minus 4x plus 4, and it's being intersected with a straight line 2x plus 4. And that then gives us two separate areas, and we are asked to calculate the shaded area. So you'll see the shaded area is a combination of this area here and this area here, and we need to calculate them separately. So in order to do that, we're going to be working with two definite integrals, and we need to know the limits of those definite integrals. So how do we get the limits? Well, what we do is we're going to find the points of intersection where these two functions cross. So this point here, I need to know that point there, and that point there. And how I get that is I set my functions equal to each other, because that's what's happening at these points. It's where the two functions have the same x value and give the same y value at that point. So I'm going to set our two functions equal to each other. So we set our cubic equal to our straight line. We're then going to collect like terms on the left hand side. So I'm going to take away 2x, take away 4 until I get to this solution here. At this point here, I've got a cubic. I might have to go to my sort of synthetic division work in order to find the solution, but it turns out this is quite a nice cubic because I can take a common factor of x out. So I'm going to take my common factor of x out from all of those terms, and now I've left myself a quadratic. I can get that factorised into two brackets, x minus 3 and x plus 2 works. And then from there, I can get three solutions for x. So my three solutions for x are 0, 3, and negative 2. So these are going to become the limits for my definite integrals. But 0, 3, negative 2, basically this point here is my negative 2. This point here is 0, and this point here is 3. So next stage, once we've got our points of intersection and our limits for using definite integrals, is to go ahead and calculate the individual separate shaded areas. The reason we need to do that is if we have a look at this area here, you'll see my top curve in this case is the cubic, and then when I move to this area, my top curve becomes the straight line. So that's going to give me a different function to be integrating with when I'm doing my definite integral. So what we're going to concentrate first on is finding this shaded area here. So that's the one we're focusing on. So that is represented by the definite integral between a lower limit of negative 2 and 0, and then my top curve, the cubic, minus my bottom curve, the straight line. So I'm going to evaluate that function first. And we've seen this before. We saw that when we were finding our points of intersection. And now I'm going to go ahead and integrate this function. So what we get there is we get x to the power of 4 over 4 minus x cubed over 3 minus 3x squared. I substitute my upper limit of 0 in and my lower limit of negative 2 in. So that's that there. I know it's not very clear in the video, but that's me basically just putting 0 in and negative 2 in. So my first term gives me 0, and then my second bracket, when I evaluate that, I get negative 16 over 3, and because I'm taking it away, that gives me an area for that first shaded area of 16 over 3. So we've just calculated this first area here as 16 over 3. So now what we do is we repeat the process for our second shaded area. So this one here, it looks slightly bigger as well. That's, I would always use the diagram to give me an idea. If this is 16 over 3, this one, we should get a bigger answer than that. So for this one here, we've got our lower limit of 0, upper limit of 3, and this time our top curve is the straight line, and our bottom curve, the one that's underneath for the area, is so we do our top curve, take away the bottom curve, so it's the straight line, take away the cubic this time. When we rearrange that to get a function that we're going to integrate, we get 6x minus x cubed plus x squared. We go ahead and we do our integration of that, and then we substitute in our upper limit of 3 and our lower limit of 0 into that new integrated function. I process that through and I get 27 for this term, 81/4 for this term, and 9 for that last one. And then my lower limit of 0 gives me a 0 in that for that second term or second bracket. And then when I evaluate this, I get 15 3/4 units. So we now have this area up here as being 15 3/4 units squared. So this 16/3, 5 1/3. This one here, nearly 3 times as big. Does it look like that in the diagram? Yeah, it probably does. So I'm pretty confident that I've probably got the right answer for these two. So our final step, fairly straightforward one. All I need to do now for the total shaded area is combine the two separate areas that I found. So my total area is going to be area 1, the smaller one, plus area 2, the bigger one. So we can write down those two areas and combine them, and we end up with a final answer of 21 1/12 units squared. And that's that example done. So a fairly complex example there. If that was in an exam, it's going to be a 10, 11, 12 marker probably. So quite a lot involved. The key thing is this idea that for each of those separate areas, we were dealing with a different function because our top curve and bottom curve changed around, they switched around at this point of intersection here. So as I say, that's probably as tough as you're going to face. It's going to allow you to get on with the remaining exercise that you were working on the other day. So the questions I would like you to do are coming up just at the end of this video.